This is 6.2.2.3. We are performing discrete time Fourier transform of a square pulse that is aperiodic. The square pulse stretches from -4 index to +4 index with an amplitude of 1. So when we want to perform the analysis of x omega, it reduces the index from only from -infinity to infinity to actually from -4 to 4. The values of xn are all 1, so we actually remove it from this equation, and the only interesting thing is x omega is a summation of these 9 values of e minus j omega n, where n will go from -4 to 4 in this example, and then we have to substitute different values of omega, the real values. You can write a very simple MATLAB code, which I have done in the next page, and you can use this MATLAB code, and by changing what are the analysis value, what are the x sequence, you can then write the code to analyze for x of omega. You realize that I am asking you to analyze omega from -pi to pi in n steps. Well, then you say that, but in the lecture notes you want for all omega from -pi to pi. Why are you asking me to do n steps of them? And that's because it's impossible for any one of us to do analysis for all omega, right? So what we do is we just divide -pi to pi into, in this example, 500 parts, and you will realize that the output is very smooth anyway, and this is what you will see for a different x. So we will generate the magnitude and the phase plot from -pi to pi, and here you see that it's -1 to 1 because we are plotting with respect to pi. So it's -pi to pi for the magnitude and for the phase. So right, you go and examine this code to see how we have done it. But let's come back to here. If you do it correctly, you will get this -pi to pi or 0 to 2 pi. It's up to you for the magnitude, and you will see that my results is the same. The phase looks very strange. You'll be very suspicious of this, and you will see that the phase sometimes go with positive values and sometimes negative values, and then if you look at these values carefully, this is pi and this is -pi. So why does this have a positive pi and this sometimes a -pi? And that is because 1e_j pi versus 1e minus j pi, what is the result? And the result is actually this is nothing but -1, and this is also -1. So basically what happened is that this value is a negative value, this is a positive value, because what is 1e_j0, this is 1, and this is negative value again, right? So the reason why you have this switching, very fast switching, is because of numerical precision, and that's the problem with many of MATLAB code. You realize that in the real world it just changes a little bit and you will get 1e minus pi or 1e plus pi, but you have to interpret this kind of results when you're an engineer. So let's start to become familiar with it now. Alright, I will leave you with this this derivation of this summation of this geometric progression to finally get this result. This is the most famous result where we have a square pulse which result into a sinc function. So this is a sinc function. So I'll repeat what is a sinc function. Sinc of k is equals to sine of k pi divided by k pi. So for this course, you ask us to know how to derive this geometric progression, and reducing this geometric progression into the sinc function, as well as writing MATLAB or Python code to take a aperiodic sequence with finite support. The word finite support means that there are only finite numbers of non-zeros, and then you can compute the absolute value of x omega as well as the angle, the phase of x omega. Okay, I've given you this code. Please play with them by changing the different x, and in fact you can change different n such that you can get different resolutions of omega as well. Now, I check out Lati's code. Lati is the author of one of the book, and he does DTFT in a single line. Alright, so this is how the expert do DTFT in a single line. With that, thank you.